A raindrop falls from a cloud about 2 kilometers up. 2 kilometers, that is higher than 6 Eiffel Towers stacked on top of each other. You with me? Good. Take any object, I do not care what it is, a baseball, a marble, a brick, drop it from 2 kilometers with nothing in the way. And by the time it reaches the ground, it is moving at about 200 meters per second. That is roughly 450 miles per hour. That is faster than a Japanese bullet train. That is faster than the takeoff speed of most commercial airplanes. That is in the neighborhood, the rough neighborhood, of the muzzle velocity of certain handgun rounds. So let me ask you something. Every raindrop in a thunderstorm starts its life way up there. Some rain clouds sit at 3 kilometers, 4 kilometers, even higher, and each one of those droplets is pulled downward by exactly the same force that would yank a bowling ball off a bridge. Gravity does not care what you are made of. Gravity does not look at a raindrop and say, "Oh, you are small, I will go easy on you." Gravity grabs everything the same way. 9.8 meters per second squared. No exceptions. So by all rights, you should be getting machine gunned every time it rains. A spring shower should put you in the hospital. A thunderstorm should be a war zone. Every single droplet, pulled for thousands of meters by the full strength of Earth's gravity, ought to hit the top of your head like a tiny liquid bullet. And yet, you walk outside in a rainstorm, and what happens? You get wet. That is it. You get a little annoyed maybe because you forgot your umbrella, but nobody is calling an ambulance. Nobody is running for the bunker. You stand there, rain pattering on your shoulders, and you feel almost nothing. That is insane. Think about what I am telling you. The math says the rain should kill you. Your daily experience says it is a minor inconvenience. Somebody is wrong. Either the math is broken, or your experience is lying to you, or there is something else going on, something big that we have not accounted for. Let me show you which one it is, and I promise you, the answer is one of the most beautiful negotiations in all of physics. Let us start with what we know for sure. Let us be very careful about this, because careful is how you avoid fooling yourself, and the easiest person to fool is yourself. Gravity near the surface of the Earth accelerates everything at the same rate. Galileo figured this out a few hundred years ago, and it has been confirmed so many times and in so many ways that we can treat it as rock solid. The acceleration is about 9.8 meters per second. That means every second you are falling, you pick up another 9.8 meters per second of speed. After 1 second, you are going 9.8. After 2 seconds, 19.6. After 3 seconds, 29.4. It just keeps climbing. So you can do the calculation. A raindrop forms in a cloud, call it 2,000 meters up. If gravity is the only thing acting on it, you use the formula. The final speed equals the square root of 2 times the acceleration times the height. Plug in the numbers. 2 times 9.8 times 2,000. That gives you about 198 meters per second. Round it to 200. 200 meters per second. How fast is that, really? Well, the speed of sound in air at sea level is about 343 meters per second. So a raindrop, if gravity were the only thing pulling on it, would hit the ground at a bit more than half the speed of sound. Not quite supersonic, but absolutely terrifying. A small rock moving at 200 meters per second would go clean through a car windshield. A raindrop at that speed would not feel like rain. It would feel like being pelted with gravel fired from a slingshot. Millions and millions of tiny impacts every second, each one carrying enough kinetic energy to sting, to bruise, to break skin. And it would be worse than that, actually, because I picked a modest cloud height. Some cumulonimbus clouds, the big thunderstorm ones, have bases at 3 or 4 kilometers, and tops that go up to 12 or 15 kilometers. The rain falling from those heights in a vacuum would be going even faster. You would need armor. So this is where we stand. Step 1 of the physics says rain should be lethal. Step 2 of your everyday experience says rain is not lethal. Something is deeply wrong with step 1. And what is wrong with step 1 is not a mistake in the math. The math is perfect. What is wrong is the assumption. We assumed gravity was the only force. We threw the raindrop off the top of a 2-kilometer cliff and pretended there was nothing between the cloud and your head. But there is something between the cloud and your head. There is air. You might think air is nothing. You walk through it, you breathe it, you barely notice it. But let me tell you something. Air is not nothing. Air is a real physical substance with real mass and real density. A cubic meter of air at sea level weighs about 1.2 kilograms. That does not sound like much, but there is a lot of air between you and the clouds. And when something tries to move through air at high speed, the air does not just politely step aside, the air fights back. Think about sticking your hand out the window of a car on the highway at 60 miles per hour. The push of the air against your flat hand is surprising. Your hand wants to fly backward. You have to work to hold it there. That push is air resistance, and it gets dramatically worse the faster you go. It does not just double when you double your speed. It goes up as the square of the speed. Twice as fast means 4 times the drag. 3 times as fast, 9 times the drag. 10 times as fast, 100 times the drag. This is a very important fact, and it changes everything about falling rain. Now, I want you to really appreciate why the velocity squared business is not just a formula someone wrote down. It tells you something true about how the air interacts with moving objects, and it is wonderfully intuitive once you see it. When a raindrop moves through the air, it has to shove air molecules out of the way. The faster the drop moves, the more air molecules it encounters per second. That is one factor of velocity. But each of those molecules also gets hit harder because the relative impact speed is higher. That is the second factor of velocity. Multiply them together and you get velocity squared. It is not a coincidence. It is not an arbitrary mathematical form. It comes from the simple geometry of how many molecules you hit and how hard you hit each one. This means that at low speed the air barely notices you. At modest speed you feel a push. At high speed, the air becomes a wall, and that wall is what catches every raindrop between the cloud and the ground. Here is what happens. A raindrop forms up in the cloud. But ding! It is tiny, just sitting there in the mist. And then it gets heavy enough that gravity pulls it loose. It starts to fall. At first, it is moving slowly, very slowly, and at that speed, the air resistance is almost nothing. Gravity is king. The drop accelerates at nearly 9.8 meters per second squared, just like any object in free fall. But as the drop picks up speed, something starts to happen. The air begins to push back. The faster the drop moves, the harder the air shoves against it. The drag force grows and grows. Meanwhile, gravity stays the same. Gravity pulls with a constant force equal to the weight of the drop. It does not get stronger just because the drop is moving faster. But the drag does get stronger, much stronger, because drag goes as velocity squared. So the drop accelerates, and the air pushes back harder. The drop accelerates more, and the air pushes back even harder. The net force on the drop, which is gravity minus drag, starts to shrink. The drop is still speeding up, but it is speeding up less and less. The acceleration is falling, and then at some particular speed, the drag force becomes exactly equal to the gravitational force. The two forces perfectly balance. At that instant, the net force on the drop is zero. Newton's second law says, if the net force is zero, the acceleration is zero. If the acceleration is zero, the velocity stops changing. The drop has reached its maximum speed. This speed has a name. We call it the terminal velocity. And it is one of the most important ideas in all of the physics of things moving through fluids, whether that fluid is air or water or oil or anything else. Terminal velocity is not something the drop chooses. It is not a speed limit imposed by some traffic law of physics. It is the natural consequence of two forces, one constant and one that grows with speed, fighting each other until they reach a draw. It is a negotiation, and both sides get exactly what they can sustain. Gravity says, I pull this hard, and I cannot pull harder. Air says, if you move at this speed, I push back exactly that hard. Neither side wins, they settle, and the drop falls at a steady, constant speed from then on. So what is that speed? How fast does a raindrop actually go? This is where the details get lovely, because the terminal velocity depends on the drop itself. It depends on the mass, the size, the shape, and the drag coefficient of the raindrop. And these are not all the same for every drop. Let us think about mass first. A bigger drop has more mass, which means gravity pulls on it harder. More weight means you need more drag to balance it. More drag only comes at a higher speed, so bigger drops fall faster. A tiny drizzle droplet, the kind you can barely feel on your face, maybe 0.5 millimeter across, reaches terminal velocity at about 2 meters per second. That is a slow walking pace. You could almost keep up with it. A typical raindrop, the kind you see bouncing off the pavement in the steady rain, might be 2 or 3 millimeters across. That one reaches terminal velocity at about 6 or 7 meters per second. Quick, but nothing dangerous. A big fat raindrop, the kind that splats loudly on a windshield, might be 4 or 5 millimeters across. That is about as big as raindrops get, and we will talk about why in a moment. That one falls at about 9 meters per second, which is roughly 20 miles per hour. 20 miles per hour from 2 kilometers up, gravity wanted to deliver it at 450 miles per hour, and the air calmly negotiated that down to 20. Think about how dramatic that is. Air resistance takes a potential killer and turns it into a gentle tapping on your umbrella. The atmosphere is not just the thing you breathe, it is a shield. A soft, invisible, ever-present shield that slows down everything that falls through it. But wait, I want you to understand something subtle here, because this is where people get confused. The raindrop does not slow down. I want to be very precise about this. If you drop a raindrop from a cloud, it never actually decelerates on the way down. It speeds up and then it stops speeding up. It reaches terminal velocity and then falls at that constant speed the rest of the way. It does not speed up and then slow down. It speeds up and then stops accelerating. There is a big difference. One means the drop is losing energy. The other means the forces are in balance. What is happening is the second one, and here is the beautiful part. For a typical raindrop falling from a cloud at 2 kilometers, it reaches terminal velocity within the first 100 meters or so of falling. After that, it has another 1900 meters to go, and it is falling at this gentle cruising speed the entire way. It is coasting. The vast majority of the drop's journey is spent at terminal velocity. The brief acceleration phase is over almost before it begins. So the image of a raindrop being dragged faster and faster and faster for 2 solid kilometers is completely wrong. The reality is that it gets a short running start, reaches its top speed very quickly, and then drifts lazily downward for the rest of the trip. And there is a beautiful energy story hidden in here that I think most people miss entirely. Think about what is happening from the perspective of energy. And that gravity is doing work on the raindrop the entire time it falls. The drop loses potential energy as it descends, and that energy has to go somewhere. In a vacuum, all of that potential energy would be converted into kinetic energy. The drop would get faster and faster and arrive at the ground with a tremendous amount of motion energy. But in air, once the drop reaches terminal velocity, it is not gaining kinetic energy anymore. Its speed is constant, yet gravity is still doing work on it. Where is all that energy going? Into the air. Every meter the raindrop falls at terminal velocity, it is doing work against the drag force. That work heats the air ever so slightly. It creates tiny turbulent eddies in its wake. It jiggles air molecules. The potential energy of the raindrop is being converted not into the raindrop's own motion, but into thermal energy of the atmosphere. The air is absorbing the energy that would otherwise make the raindrop dangerous. A single raindrop releases a very tiny amount of heat this way. But think about a thunderstorm that drops, say, 50 millimeters of rain over a large area. Billions upon billions of drops, each one converting gravitational potential energy into heat in the atmosphere. The total energy transfer is enormous. It is one of the many ways that weather redistributes energy around the planet. The rain is not just bringing water down, it is bringing energy down, and the air is soaking it up on the way. Now I want to show you something else that most people get wrong, and it is a delightful thing to get wrong because the truth is so much more interesting than the myth. I am talking about the shape of a raindrop. Ask a child to draw a raindrop and they will draw a teardrop. Pointed at the top, round at the bottom, like a little liquid flame. You see this shape everywhere. Weather reports, decorations, cartoons, logos. Everybody knows what a raindrop looks like, and everybody is wrong. A small raindrop, less than about a millimeter across, is a nearly perfect sphere. It is a tiny round ball. Surface tension holds it together, the same force that makes water bead up on a waxed car. The water molecules on the surface are pulling inward, trying to minimize the surface area, and the shape with the least surface area for a given volume is a sphere, so small drops are round. As the drop gets bigger, gravity and air resistance start to compete with surface tension. A drop 2 or 3 millimeters across is still roughly round on top, but the bottom gets flattened. The air rushing past underneath pushes up on the bottom face. The drop starts to look like the top half of a hamburger bun. Rounded on top, flat on the bottom, not a teardrop at all. The exact opposite of what you would expect. And when a drop gets really big, bigger than about 4 or 4.5 millimeters, something dramatic happens. The air pressure on the bottom creates a dimple, then a cavity. The drop starts to look like a tiny parachute or a jellyfish, with a thin film of water stretched across the top and a thicker ring of water around the rim. It is completely unstable in this shape. Within moments, the thin film ruptures and the big drop explodes into several smaller drops. This is why you never see raindrops bigger than about 5 millimeters. Nature has a speed limit for raindrop size, and that limit is enforced by air resistance and surface tension working together. This breakup business is important because it explains something else. If all raindrops started huge, up in the cloud and grew as they fell, you might eventually get enormous drops hitting the ground. But they cannot survive. The bigger they get, the faster they fall, the more the air deforms them, and at some point they shatter. So the rain that reaches you is always in this narrow range. Not too small to fall, not too big to hold together. Nature has filtered it for you, and every single one of those drops, regardless of size, has found its terminal velocity long before it reaches the ground. Let me come back to the physics for a moment, because I want you to see the machinery that makes this work. The drag force on an object moving through a fluid depends on a few things. First, it depends on the density of the fluid. Denser fluid means more drag. Swimming through honey is harder than swimming through water, and swimming through water is harder than moving through air. Second, it depends on the cross-sectional area of the object, the area it presents to the flow. A parachute has more area than a marble, so it gets more drag. Third, it depends on the speed squared, as we talked about. And fourth, it depends on something called the drag coefficient, which is a number that captures the shape and smoothness of the object. A sleek sports car has a low drag coefficient. A brick has a high one. A flat plate perpendicular to the wind has an even higher one. For a roughly spherical raindrop, the drag coefficient is about 0.5. That is somewhere between a smooth sphere and a rough one. It is not a bad number. Nothing exotic. Just an ordinary shape doing its ordinary thing in ordinary air. Now let me do a thought experiment that makes the formula come alive. Imagine you have two raindrops. One has twice the radius of the other. How do their terminal velocities compare? The big drop has 8 times the volume, and since water has a constant density, it has 8 times the mass and therefore 8 times the weight. Gravity pulls it 8 times harder. The cross-sectional area, though, only goes as radius squared. So the big drop has 4 times the area. At the same speed, it would feel 4 times the drag. But to balance 8 times the weight, it needs to feel 8 times the drag. So it needs twice the drag per unit area. But since drag per unit area goes as velocity squared, twice the drag per unit area means the velocity has to go up by a factor of the square root of 2, which is about 1.4. So the bigger drop falls about 40% faster. Not twice as fast. 40% faster. That is the square root of radius scaling in action. Now, at terminal velocity, the drag force equals the weight. The weight of a spherical drop goes as the cube of its radius, because weight is proportional to volume, and volume goes as radius cubed, but the drag force depends on the area, which goes as radius squared, and on velocity squared. So at terminal velocity, you can set these equal and solve for velocity, and you find that terminal velocity goes roughly as the square root of the radius. This means bigger drops fall faster, but not linearly faster. Double the radius and the terminal velocity goes up by a factor of about 1.4, not 2. There is a diminishing return. Giant drops are faster, but not spectacularly faster. Let me put some specific numbers on this because numbers sharpen the picture. A fog droplet, maybe 1/10 of a millimeter across, falls at about 1/4 of a meter per second. That is practically stationary. It hangs in the air like a whisper. This is why fog does not rain on you. The drops are so small and so light that even the faintest updraft can hold them aloft. A drizzle drop about 1/2 millimeter falls at roughly 2 meters per second. This is a casual stroll. You could outpace it if you walked briskly. Drizzle does not feel like drops hitting you. It feels like the air itself is damp. That is because the drops are so slow and so fine that they are more like a wet mist than a rain. A medium raindrop, the kind that makes puddles on the sidewalk, is about 2 millimeters across and falls at roughly 6.5 meters per second. That is about 15 miles per hour, about the speed you ride a bicycle. A big raindrop, 3 or 4 millimeters, one of those fat drops that makes a satisfying splat, reaches about 8 to 9 meters per second. That is around 20 miles per hour. You feel these when they hit. They make a sound, but they do not hurt. And the very biggest drops, the rare monsters that push 4.5 or 5 millimeters, max out at roughly 9 meters per second before they blow apart. Nature puts a ceiling on the whole system. So the entire range of raindrop terminal velocities, from the finest drizzle to the fattest drops, spans roughly from 2 to 9 meters per second. That is the whole story. 2 to 9. Every raindrop on Earth, every rainstorm you have ever experienced, every downpour and sprinkle and mist, all of it falls within this narrow band of speeds. And this is why all raindrops, despite coming in a range of sizes, all arrive in roughly the same speed neighborhood. The smallest drizzle drops come in at around 2 meters per second. The biggest possible raindrops come in at around 9. The ratio between the slowest and the fastest is less than 5 to 1. They are all in the same ballpark, all gentle, all survivable, all negotiated down from potential catastrophe by the same mechanism. There is something philosophically satisfying about this. Nature did not need a special rule to protect you from murderous rain. No new force was invented. No exception was carved out. The same laws of motion that govern planets and cannonballs and electrons govern raindrops. It is just that when you apply those laws carefully, accounting for all the forces, you discover that the universe is gentler than the naive calculation suggests. The atmosphere is not just decoration, it is an active participant in every fall, every flight, every throw, and its participation in the case of rain turns a bombardment into a shower. Now here is something I find irresistible when I think about this topic. What about other worlds? What about rain on other planets? On Mars, the atmosphere is about 1% the density of Earth's. 1%. If it rained water on Mars, and it cannot because Mars is too cold and too dry, but if it could, those raindrops would have dramatically higher terminal velocities. The thin Martian air would barely slow them down. A raindrop on Mars might hit at 50, 60, 70 meters per second. You would need serious shelter. On Venus, the opposite problem. The atmosphere is incredibly thick and incredibly hot. The atmospheric pressure at the surface of Venus is about 90 times Earth's. It does rain on Venus, sort of. Sulfuric acid droplets form in the upper atmosphere and begin to fall. But they never reach the ground. The temperature rises so steeply as you descend through that dense atmosphere that the drops evaporate before they arrive. Venus has virga, rain that never lands. And if it somehow did land, the extreme density of the atmosphere would give those drops an incredibly low terminal velocity. They would float down like feathers in honey. And then there is Titan, the big moon of Saturn. Titan is one of the most remarkable places in the solar system. It has a thick atmosphere, about 1.5 times the surface pressure of Earth's, and it rains on Titan. It rains methane. Liquid methane falls from methane clouds onto a surface covered with methane lakes and methane rivers. The gravity is weaker there, only about 1/7 of Earth's, and the atmosphere is denser. So methane raindrops on Titan would fall very slowly indeed, maybe about 1.5 meters per second for a big drop, walking speed. You could stand in a methane rainstorm on Titan, and the drops would land on your helmet so gently you might not even notice. The physics is the same everywhere. Gravity pulls, drag resists, terminal velocity is reached. But the specific numbers, the density of the atmosphere, the strength of gravity, the properties of the liquid, those determine whether rain is a gentle mist or a punishing assault. Earth sits in a very comfortable spot, just enough air to make rain safe, just enough gravity to bring it down. The balance is nothing short of remarkable. Let me give you a feeling for just how efficient this air resistance is on our planet. Suppose a raindrop starts from rest at 2,000 meters. In a vacuum, it would take about 20 seconds to hit the ground, arriving at roughly 200 meters per second. In air, the same raindrop takes several minutes. Several minutes. It is moving at 9 meters per second for almost the entire trip, which means it takes roughly 3.5 minutes to cover 2,000 meters. The air has slowed the arrival time by a factor of 10, and slowed the impact speed by a factor of more than 20. Now you might ask, well, what about other things that fall through the atmosphere? Do they all get this kind of protection? And the answer is, it depends on what you are. A skydiver, for example, falls much faster than a raindrop. That a human being in free fall reaches a terminal velocity of about 55 meters per second, or about 120 miles per hour in the spread eagle position. That is because a person is much heavier relative to their cross-sectional area than a raindrop is. More weight relative to drag means you have to go faster before the drag catches up. This is why skydivers need parachutes. Their terminal velocity is survivable, but unpleasantly so. A hailstone. Now there is an interesting case. Hail is ice, so it is denser than a raindrop, and it is often larger. It also does not deform and break up the way water drops do, because ice is rigid. A hailstone holds its shape. A big hailstone, say 5 centimeters across, can have a terminal velocity of 30 meters per second or more. That is about 70 miles per hour, and that hurts. That dents cars. That cracks windshields. That strips leaves off trees. So the air does slow it down. Very much so. Without air resistance, a hailstone from 10 kilometers up would hit at roughly 440 meters per second, well into the supersonic range. The air knocks that down to 30 or 40 meters per second. That is a huge reduction, a 90% reduction or more. But 90% is not quite enough when you start with a stone the size of a golf ball traveling faster than sound. Hailstones are one of those cases where air resistance helps enormously, but still cannot make the thing harmless. Contrast that with a snowflake. A snowflake is light, fluffy, full of air pockets, and has an enormous surface area relative to its tiny mass. A snowflake's terminal velocity is about 1 meter per second. Sometimes less. It drifts down like a leaf on a calm day. You can watch it meander and swirl and change direction with every tiny current of air. The drag coefficient of a snowflake is very high because of its complex branching shape, and its mass is minuscule. The negotiation between gravity and air is so lopsided in favor of the air that the snowflake barely falls at all. And think about dust. A tiny speck of dust falls so slowly through the air that it can take hours to settle from head height to the floor. Its terminal velocity might be a centimeter per second or less. The air resistance is overwhelming compared to the minuscule weight. The particle essentially floats. It drifts. It can be carried sideways by the slightest breeze. So, terminal velocity is not one number. It is a spectrum. And where you land on that spectrum depends on the negotiation between your weight and your drag. Light things with big area fall slowly. Heavy things with small area fall fast. And raindrops sit in a sweet spot where they fall fast enough to reach the ground in a reasonable time, but slowly enough that you can stand in them and barely notice. There is one more twist I want to show you, because it comes from something that happened in science fairly recently, in the early 2000s. For a long time, everybody assumed that every raindrop hits the ground at terminal velocity. It has had plenty of time to reach equilibrium, and it is falling steadily. The basic theory was settled. Gunn and Kinzer, 2 researchers, published very careful measurements of raindrop terminal velocities back in 1949. They dropped water drops of known sizes in a tall laboratory tower and measured exactly how fast they fell. Their data became the gold standard. For decades, meteorologists used their numbers to estimate rainfall from radar measurements. You see a certain size drop on radar, you look up its terminal velocity in the Gunn and Kinzer table, and you calculate how much rain is falling. That was the standard picture. Clean, tidy, done. But then some researchers at the College of Charleston set up an array of very sensitive instruments and high-speed cameras outdoors in real rainstorms. And they watched millions of actual raindrops arrive. Not laboratory drops falling in still air, but real drops falling through real turbulent weather. What they found was surprising. The large drops, the ones bigger than about a millimeter, behaved exactly as expected. They arrived at their predicted terminal velocities, plus or minus a little scatter from wind and turbulence. No surprises there. But the tiny drops, the ones smaller than about half a millimeter, were moving faster than their terminal velocities predicted. Quite a bit faster in some cases. More than 1.3 times the expected speed. How could that be? How can something fall faster than its terminal velocity? The answer, they think, is breakup. A big raindrop falling at its higher terminal velocity shatters in the air. The fragments are small, but they do not instantly slow down. They were part of a big drop that was moving fast, and now they are little drops that should be moving slowly, but they have not had time to decelerate yet. They are tiny drops carrying the momentum of their bigger parent. They are moving at a speed that does not match their size. So when these fragments hit the instruments, they register as small drops moving faster than they should. They are not violating physics, they are obeying physics perfectly. They are simply carrying the history of their origin. They are small drops that recently used to be part of something bigger and faster. They have not yet forgotten where they came from. I love this because it tells you that even something as simple as rain falling from the sky has layers of complexity that can surprise you. You think you understand terminal velocity, and you do. But then nature shows you that the real world does not always give you clean equilibrium conditions. The real world has collisions and breakups and fragments carrying memory, and the physics has to account for all of it. This also matters practically, by the way. Meteorologists estimate how much rain is falling by measuring raindrop sizes and assuming each drop is at its terminal velocity for that size. If a significant fraction of small drops are actually moving faster than expected because they are fresh fragments of bigger drops, then the standard conversion from radar data to rainfall rate might be slightly off. It is a small effect, but rain measurement matters enormously for flood prediction, agriculture, climate science, and water resource management. Even a seemingly academic discovery about tiny speeding droplets can ripple outward into real-world consequences. That is how science works. You start with curiosity about something that seems trivial, and you end up improving weather forecasting. You never know where a question will take you until you follow it. Let me step back now and think about what this story is really telling us. We started with a simple calculation. Gravity pulls a raindrop, the raindrop falls, it should hit hard. That calculation was not wrong. It was incomplete. It left out a major player, and when we added that player, air resistance, the answer changed dramatically, from lethal to harmless, from 450 miles per hour to 20, not a small correction, an enormous one. This is one of the most important lessons in all of physics, and it has nothing to do with rain specifically. The lesson is this: when your calculation gives you an absurd answer, do not throw out the physics. Check your assumptions. Almost always you left something out, and the thing you left out might change everything. This happens over and over again in the history of science. People get ridiculous answers, and instead of blaming the universe, they blame their own model. And they are right to. The universe is not ridiculous. The universe does what it does, perfectly consistently, every single time. If your prediction does not match reality, reality is not the one with the problem. Lord Kelvin, back in the 19th century, calculated the age of the Earth based on how long it would take a molten ball to cool down. He got an answer of about 20 to 40 million years. The geologists and the biologists were screaming that this was way too short. Evolution needed more time. The rock record needed more time. Kelvin was sure of his physics, but his physics was incomplete. He did not know about radioactive decay, which is an internal source of heat. When you add that in, the Earth can stay warm much longer, and the real age turns out to be about 4.5 billion years. His mistake was not in his equations. His mistake was in his assumptions. He left out a heat source. This is the same kind of error we made with the raindrop. We left out a force. And when you leave out a force that matters, your answer can be catastrophically wrong. In this case, the missing ingredient was obvious once you looked for it. Of course, air matters. We live at the bottom of an ocean of air, a blanket of gas about 100 kilometers thick, held down by gravity. Everything that moves through it feels its presence. Everything, raindrops, snowflakes, baseballs, birds, bullets. Every object negotiates with the air. And the terms of the negotiation depend on the specifics of the object and the specifics of its motion. I sometimes think of it this way. Imagine the atmosphere as a kind of invisible mesh, a net made of bouncing, jittering molecules, packed pretty tightly at sea level. About 25 billion molecules in every cubic centimeter. If you try to push through that mesh slowly, the molecules just drift out of your way. You barely feel them, but push through fast, and the molecules cannot move aside quickly enough. They pile up in front of you. They slam into you. They create a pressure, a wall of resistance, that scales with the square of how fast you are going. The mesh is always there, but you only notice it when you try to move quickly. A raindrop falling through this mesh from 2 kilometers up would love to accelerate to 200 meters per second. Gravity is pulling it, urging it on, but the mesh says, not so fast. Every meter per second you gain, I push back 4 times harder, and by 9 meters per second I am pushing back exactly as hard as gravity is pulling you forward. Stalemate. The drop can go no faster, the mesh has won. But there is a deeper point here too, and it is about the nature of forces. In the introductory physics class, we usually start with gravity, and we ignore air resistance. We say, imagine there is no air. This is useful because it lets you see the simple, clean behavior of gravity without the complication of drag. You learn that all objects fall at the same rate in a vacuum. You learn the parabolic trajectory. You learn conservation of energy for gravitational problems. These are real things, and they are important. But the danger of that simplification is that students sometimes forget it is a simplification. They start to think that the vacuum calculation is the real answer, and air resistance is just a small fudge factor you add at the end. For a cannonball or a bowling ball over short distances, that is approximately true. Air resistance is a small correction. For a raindrop over 2 kilometers, air resistance is not a correction. It is the dominant effect. It reduces the impact speed by more than 95%. If you ignore it, you do not get an approximate answer. You get a completely wrong answer, an answer that is off by a factor of 20, an answer that predicts lethal rain. So the lesson is, know when your simplifications are safe and when they are dangerous. Know when you can ignore something and when you cannot. The physics does not care about your assumptions. The physics includes all the forces, all the time. It is your job as the person doing the calculation to decide which ones matter. And the only way to decide which ones matter is to have some physical intuition about the system. How do you develop that intuition? By doing exactly what we just did. By taking a situation, making a naive guess, comparing it to reality, finding the discrepancy, and figuring out what you missed. That cycle, over and over, prediction and surprise and correction, that is how you learn to think like a physicist. Not by memorizing formulas, by getting things wrong and then understanding why. Let me leave you with one more thought because I think it is the most wonderful part of this whole story. Right now, at this moment, there are rainstorms happening somewhere on the planet. Billions and billions of raindrops are falling from clouds, pulled by gravity, slowed by air. Every single one of them is engaged in this negotiation. Every single one is reaching its own personal terminal velocity, determined by its own mass and shape and size, and every single one is arriving at the ground gently enough that the world below it keeps going. Rivers fill. Crops grow. People walk to the bus stop and get a little wet and complain about the weather. None of that could happen without air resistance. Without the atmosphere slowing rain to a gentle patter, the surface of the earth would be continuously sandblasted by high-speed water. Soil would erode instantly. Lakes would churn. Nothing delicate could survive. Life, at least life as we know it, depends not just on the existence of water, but on the existence of an atmosphere thick enough to gentle that water's arrival. So the air you are breathing right now is doing double duty. It is keeping you alive from the inside by providing oxygen, and it is keeping you alive from the outside by catching every raindrop before it can hurt you. That invisible stuff that you walk through without thinking, that you push aside with every step, is a lifeline. It is a buffer between you and the raw, unchecked power of gravity acting on water. And the physics that governs this is not exotic. It is not quantum mechanics or general relativity or string theory. It is Newton's laws and a drag force that goes as velocity squared. It is freshman physics, applied honestly. The simplest laws, the most basic forces, combining in a way that just happens to make the world livable. That is what I find so staggering. You do not need anything fancy to explain why you can walk in the rain. You need gravity and drag and Newton's second law. But you have to actually use them. You have to add them up honestly. And when you do, you find that the universe, running on these plain, boring, everyday equations, has built itself a system where water can fall from the sky and land softly. No engineer designed it. No committee voted on it. The laws just work out that way. And I think this is part of what makes physics so thrilling. Not the exotic stuff. Not black holes or quantum entanglement or particle accelerators, though those are marvelous too. What thrills me is the ordinary stuff, done honestly. A drop of water falling through air, two forces in competition, a speed that balances, a gentle tap on your shoulder instead of a bullet through your skull. The physics was there all along, sitting in Newton's laws, waiting for you to apply it properly. There is a tendency, I think, especially among students, to believe that the interesting physics is always the hard physics. The graduate level stuff, the abstract stuff. But some of the most profound insights come from taking a very simple question seriously. Why does rain not kill you? It sounds silly. It sounds like something a child would ask. But when you sit down and actually work it out, you discover terminal velocity, the velocity squared drag law, energy transfer to the atmosphere, breakup dynamics of large drops, the scaling of survival with body size, and the atmospheric conditions necessary for gentle precipitation. Or from a question a 6-year-old might ask. Never dismiss a simple question. The simplest questions often lead to the deepest answers. I have found this to be true over and over in my own work, and I commend the practice to you. Isn't physics something? The same equations that describe planets and pendulums and springs, these tired old equations that every student has seen 1,000 times, those exact equations explain why you are not riddled with holes every time it rains. You just have to trust them. You just have to apply them completely. Next time you are outside and it starts to rain, before you reach for the umbrella, stand there for a second. Feel those drops land. Each one has fallen for 3 or 4 minutes from a cloud way up there. Each one started its journey in free fall, accelerating like every other falling object, and each one was caught by the atmosphere and slowed to a gentle tap. That tap on your forehead is the sound of a negotiation, worked out between gravity and air, between weight and drag, resolved peacefully in midair, long before it reached you. So here is something to think about. We said that terminal velocity depends on mass relative to area. A raindrop falls slowly because it is light for its size. Now think about this. What if you could shrink yourself down to the size of an ant? Your mass would decrease much faster than your surface area. Your terminal velocity would become very, very small. You could fall from any height and land unharmed. An ant dropped from the top of the Empire State Building reaches the ground at roughly 2 meters per second. A cat might survive the same fall. A human would not. The same laws, the same air, the same gravity. Completely different outcomes depending on the ratio of mass to area. What does that tell you about the way size governs survival? And what does it say about the kind of creatures that could thrive on a planet with a thinner atmosphere or a thicker one? Think about it. I would love to hear your answer.